Embedding reinforcement within a concrete model is vastly simplified by the parasitic bar facility, new in version 21. This allows us to define the geometry of the concrete as an outline only and parasitically attach the reinforcement, defined as a bar element taking tensile or compressive loads. In this 2D model of a reinforced concrete hinge, I've created my concrete outline and meshed it already. We then need to define our reinforcement geometry using lines. As with all geometry in LUSAS, this could be created within LUSAS or imported from an external file. We can import multiple different file types. I'm going to bring in my reinforcement from a CAD package via DXF. We then need to define our mesh for the reinforcement, and this one uses the new parasitic bar option. When we assign the mesh attribute to the lines, LUSAS then automatically determines the intersection and connections between the bar elements and the concrete elements, which in this model are 2D plane strain elements. The fact that LUSAS is now able to determine the mesh intersections while retaining the simple concrete outline geometry means that should you wish to change the reinforcement in order to consider a different layout, it's incredibly simple as your concrete geometry remains unchanged. Now that LUSAS has completed the meshing process, let's assign our bar diameters. These are normal line cross-section attributes, and I'm using a 12mm bar throughout for simplicity of assignment in this demonstration. But obviously, you can assign different diameters to different lines to give an accurate reinforcement gauge. Let's assign materials. And then click Solve. While it's solving, we can talk a bit about the materials I'm using in this analysis. For the concrete, I'm using a non-linear cracking and crushing material, proprietary to LUSAS. In this material, we can define the limiting tensile stress, beyond which cracking will occur, as well as the compressive strength, beyond which crushing will occur. The steel material uses a von Mises yield criterion, beyond which increasing deformation can occur without an increase in stress in the steel. These non-linear materials allow us to model the behavior of reinforced concrete, where localized concrete cracking can lead to the tensile load being taken by the reinforcement, which if loaded enough, will yield. Let's look at some results. We'll turn on the contours layer for stress within the reinforcement. We'll turn off the geometry layer to clean up the image a bit, and we'll switch from the mesh layer to the deformed mesh. Lastly, let's turn on the values layer for stress, cracking and crushing in order to see a visualization of black lines showing crack planes, and if there are any crushing areas, these will be shown with black stars. If we zoom in on the hinge location, we can see cracking in one side of the hinge and the reinforcement yielding where the concrete is cracked. This demonstration has been with a 2D model, but the same principles apply within a 3D model too. If we switch to an example model, here I have 3 simple volumes defined for my concrete. The reinforcement is defined by line geometry, unconnected to the volumes, but by using the parasitic bar elements, LUSAS is once again able to intersect the bar elements with the concrete volume elements. Advanced concrete analysis with embedded reinforcement, simplified in LUSAS version 21.